6.3a, we are going to introduce vectors today. So imagine you're standing outside. So imagine you're just standing outside and you feel a gust of wind, right? You feel a gust of wind and it's pushing you in a certain direction, whether it's left or right. You feel the wind. But here's the thing. The wind doesn't just push you in one straight line, in a perfect XY coordinate, right? If this was you, the wind just doesn't push you in one way or the other. The wind is ephemeral. It pushes you in other directions. And that particular direction, so that force that it's pushing you, how do we define that force? Well, that force, even though it's a push wind, it is kind of two-dimensional. So it has a X and a Y coordinate for it. So today we're going to talk about vectors. And vectors is covered a lot in physics and science when they talk about force and motion and direction and magnitude. They cover vectors. So first things first, let's say we have a vector, and the vector has a y and x coordinate, and the vector is basically, if you think about a force. So let's say the wind is pushing this direction here, and this is our vector, and that direction has a coordinate. It has a -6 and -1 as a coordinate. Well, first, let's think about its component form, right? The component form, when we write for vectors, is a kind of angular bracket. And so that is a -6 and -1. When we talk about the magnitude, first things first, magnitude is always, it is an amount of force, so it is always positive. When we put into the direction, we no longer just talk about magnitude. The direction then is the force itself. But when we just talk about magnitude, we talk about how much it's pushing. We don't care what direction it's going in. We just care about how much. And to do that, we use the distance formula to denote magnitude. So here, the distance formula, the magnitude is the same thing as saying the square root of -6 squared plus -1 squared. That will give us the square root of 36 plus 1, which is the square root of 37. So the magnitude is the square root of 37. The component is -6, -1. What if it didn't start at the origin, right? It's so easy to discuss about when it starts at the origin. But let's say this vector started somewhere else. Let's say the vector started here. Its initial point is going to be at -1, 7. And then let's say the terminal point is here. Which is, let's say, 6, -17. Let me rewrite -17 so it looks actually like a 17. And so if we draw the arrow, it kind of looks like this, right? That would be our vector. So how do we write the component here? Well, we kind of, if you think about this and we want to move this dot to the origin, what we do is to write the component, we find the difference. So the component here is then the difference between its terminal point to its initial point. So here, if I were to put in that component, I would take 6 minus -1 and -17 minus 7, which gives me 7 comma -24. So that would be the actual component form of the true vector if it was starting from the origin. So that's how you'd find the component. So now, once we find the component, we can find the actual magnitude. So the magnitude, using the distance formula, or the magnitude, this V, equals, and I'll just use my component. So we get 7 squared plus -24 squared, square root both of that. That gives us the square root of 49 plus 576, which is then the square root of 625, and 625 is a perfect square. It is 25. So the magnitude is 25. Our component is 7, -24. What if we had two forces? So let me move this down a little bit further, and let's discuss what would happen if we had two forces acting upon the same object, because you don't always have just one force acting on you. Sometimes, if you ever see a feather fall down, the force of gravity is pulling it down, but there might be a wind pushing off to one particular direction. So it's kind of falling at angular position. So let's say we have two vectors, okay, and we'll call those vector u, and the component of u is 3, 6, and a second vector v, and the component of v is 7, 0. First things first, what would be the combined? So u plus v. So if the two forces combine, what would that look like? Well, to do that, we just need to draw u and v, and then we combine them together. So here, think about where u and v has to be. So u is 3, 6. So if I graph this, I'm gonna make this 3. 1, 2, 3, 4, 5, 6. So 3, 6. So this is u. And v is 7, 0. So this goes over 7. 1, 2, 3, 4, 5, 6, 7. So this would be v. If I combine them together, we can just attach v. So I can either attach u to v, but I'm going to start where u is at, and then this v, notice it goes over 7. So 1, 2, 3, 4, 5, 6, 7. So at the point of u, I'm going to go over 7. So 1, 2, 3, 4, 5, 6, 7. We'll just invade this graph over here. And this is the equivalent of u plus v. And also, the component of u plus v, you just have to add these points. But you can also see on the graph, it is also 10, 6. What about u minus v? So let's u minus v. maybe I'll use a different graph this way. They don't interfere with each other. But I want u minus v as a reference. So let's say this is u minus v. Well, first we'll start with u, our original graph here. But now v is going in the opposite direction when we graph u minus v. So v was going to the right. So now v is going to go to the left 7 coordinates. And then they're combined. If I took u and I took the kind of like the equivalent of u from the end of v and I did a little dot, dot, dot here, and it would make a parallelogram, the combined u minus v would actually be here because we want it to go towards the second quadrant, because notice this is going this way. It's kind of in between the two. We also just would then subtract the components of 3 minus 7 and 6 minus 0. So that would be 3 minus 7 and 6 minus 0, which will give us a component of -4, 6 for u minus v. Lastly, what if we had something really different? What if we had over here, well, we have 2u minus 3v. So u is twice the force that it was, and v is 3 times the force that it was. So let's first look at the components of u. U is 3, 6. Once again, 3, 6. And v is 7, 0. Well, 2u is everything twice that. So then it is 6, 12. And 3v, well, isn't that just 21, 0? I'm going to redo my amounts. So I'm going to go in, we'll say 3s. So here, so this is 3, this is 6, this is 6, and then go up 12, 3, 6, 9, 12. So this is 12. So this will be u right here, and well, 2u, and then 3v, we're subtracting, so we're going the opposite direction this way. So 21, so 3, 6, 9, 12, 15, 18, 21, all the way over here. And then we'll just do a dot, 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 make a parallelogram. This is the graph of 2u minus 3v. And we can just subtract this. The component is then 6 minus 21 and 12 minus 0, which gives us a -15, 12 for the component of 2u minus 3v. Also, we can rewrite this in terms of i's and j's if we want to do the resulting vector, and we want to rewrite this not in component form but as a linear combination. And to write that as a linear combination, we would say -15i plus 12j. I goes first, j goes second.